we're very happy to have Dallas Albritton from Princeton talk to us about non-uniqueness. So thank you.
Thanks a lot, Theo. So, I'm very happy to be here. It's really my pleasure. When I was a graduate student, yeah, Theo was at Princeton. So you're just talking about, did I take Theo's place at Princeton? Yeah, Theo was at Princeton and was organizing the fluid seminar, invited me out. And this was really eye-opening, and that was a very helpful visit. And so now we're having, part two, if you like. So, okay, so very good. I'm going to talk. I mean, this is a very bold title. Okay, I'm not going to. I think I'm actually setting myself up for failure with this title: Instability, Non-uniqueness, and Unpredictability in the Partial Differential Equations of Fluid Dynamics. It's a little bolder than we're able to prove, but there's some kind of. We can prove the first two things, and the last thing we have some conjectures about. Let me tell you about it. So we don't all work on, we don't all think about Navier-Stokes here every day. I mean, I think about Navier-Stokes probably every day, but since we should review. Okay, so what are the Navier-Stokes equations? They're a mathematical model. They describe the motion of a viscous incompressible fluid, and they work really well across a wide range of regimes. So what are the equations? This is the first equation. It's conservation of momentum. U is the fluid velocity field. We think.
We're saying the second two terms are the force.
We are saying the second.
Force equals acceleration.
We are saying that these are also acceleration because I've divided by the density. So the mass here has been divided out. This is now. So it's now acceleration equals acceleration. But yes, this is F equals ma. Yeah. So use the fluid velocity field, namely at every point in space-time, there's a little vector which tells you at that point in space and at that time how that fluid particle is moving. P is the other unknown. It's the scalar pressure, and these are the two unknowns. Nu is the viscosity, and it sits in front of this Laplacian term, nu Laplacian u. This is called the viscous term. And you can think of it as if you have different layers of fluid which slide across each other, then there's some friction force which wants to act against this. This is one way to think of the term. Lastly, there's this rho. Rho is a constant. It's the density. I really put it on the slide so people could make sense of F equals ma if they want to really think through it. It's a constant, and it stays constant. The reason it stays constant is actually because of this incompressibility condition. Incompressibility says that if you have some parcel of fluid which gets evolved forward, so it moves somewhere, it changes shape, it doesn't change its volume. That's captured in divergence u equals 0. So if you start with constant density, it's actually kept, and then we stop talking about rho. It's not very interesting. So these are the Navier-Stokes equations. They're the protagonists of today's talk, if you like. The Navier-Stokes equations, they hide a lot of interesting phenomena, which you may have a hard time extracting out of the equations. So one of them is the instability of certain interesting steady states. I want to introduce a number called the Reynolds number. This is a dimensionless number. It roughly characterizes the flow regime. And as an example, I'm going to use flow past a cylinder. So what we're looking at here is a numerical simulation of a cylinder. So we think like this, and you're looking at it top down. And maybe you're over here. You're looking at it top down, and the flow is running past it like this, with a characteristic velocity of we call it capital U. L is the diameter of the cylinder, and nu is the viscosity. This was the constant in front of the friction term, right? So Lu over nu is dimensionless, and it's approximately the ratio between the inertial terms, that's u grad u, over the viscous term. So at low Reynolds, viscosity is dominating. At high Reynolds, the inertial term is dominating. All right, so I want to watch a video of what's going on in this crossflow.
Is everything constant in the vertical direction?
Let's say everything's constant in the vertical direction. And this For low Reynolds, that's kept, and for high Reynolds, this will be violated. But all right, so when the Reynolds number is very small here, you have Reynolds number 4, you're going to see a steady Navier-Stokes solution. Now that doesn't mean that the particles aren't moving. The particles are moving. It's that the velocity field doesn't change. And the flow, the particles travel on these lines, which we call streamlines. They're all well organized into layers, so we call the flow laminar. This means organized into layers. When you start to increase the Reynolds number, then you'll still see a steady Navier-Stokes flow. You'll start to see these regions behind the cylinder, these recirculation regions. If you're a little particle, you can get trapped here. But the flow is still laminar. If you increase the Reynolds number enough, you will stop seeing this steady flow. You'll start to see a time periodic flow, which exhibits what we call vortex shedding. So it's like you have a vortex up here. It comes off and it travels downstream, followed by another one, comes off, travels downstream. And if you increase the Reynolds number, you can see further bifurcations. The vortex, the frequency of the vortex shedding increases. And this is like the path to turbulence. Something I want to mention about this picture is that, even when you go to these higher Reynolds numbers, this steady Navier-Stokes solution still exists, like as a solution of the PDE. You won't see it in nature because it's become unstable. It exists, but it's unstable. This time periodic motion is the stable one. The flow has undergone what's called a Hopf bifurcation. So, this solution would still exist. You just won't see it. This is going to be a point which I'll come back to.
What does the color stand for?
Sorry?
What does the color stand for?
The color. What does the color stand for? The color stands for. That's a good question. The color stands for.
Maybe it's vorticity.
It might be vorticity, but I also don't want to, go on record saying that. But let's say it's vorticity. Okay. All right. So very good. So that's this phenomenon which lurks in the equations. So I want to mention something about what happens when you really crank up the Reynolds number. So we were just looking at Reynolds number 180. This is Reynolds number 22,000. And it's not the exact same configuration. This is flow past. It's still a cylinder, but it's now a square cylinder. If you crank up the Reynolds number this is like the Reynolds number of a fastball. If you're looking at the flow around a vehicle, that's the Reynolds number in the millions. So these large Reynolds numbers are really relevant. Then the flows, they become three-dimensional, and they develop very small length scales in the turbulent wake. The length scale is like Reynolds to the minus 3/4. And this lets you estimate the number of grid points you would need to fully resolve the flow. The number of grid points would be like Reynolds to the 9/4. It's a huge number. It's very difficult to simulate these. There's a whole art around it in science. And one of the points I want to make here is that for a Reynolds number for like flow around a car, if you really want to simulate everything exactly, you will still have difficulty doing it even with modern computational power. And I think this is interesting. This is not really the full case I want to make, but I want to make this helps you make the case that you should try to understand as much as you can with theory before just putting everything on the computer. So with that in mind, I want to give you a rapid tour of the PDE theory of the Navier-Stokes equations. So Navier-Stokes, the PDE is supposed to be a self-consistent deterministic model which you would use to predict the motion of a fluid. Namely, if I know everything about the fluid right now, I'd like to be able to say everything about it 1 second from now. As mathematicians, this question becomes a question of global well-posedness. If I start Navier-Stokes with smooth initial data, is there a smooth solution for all time? Or is Navier-Stokes globally well-posed? Now, for PDE people, well-posedness is a kind of package. It means for every data, there exists a solution. the solution is unique, and also it depends continuously on the initial data. If I jiggle the initial data a little bit, the solution will only jiggle a little bit. So this is a fundamental question. If you start with an initial velocity in LP, p bigger than 3, then you have local well-posedness. So for some short time, there's a solution. But you don't know whether you can continue this solution for all time. I have some heuristic here for why p equals 3. This is somehow relevant. But it has to do with balancing the terms in the equation. Let's say the velocity field looks like 1 over x to the kappa. You plug this into the various terms to see what's going to govern the evolution. So you plug this into u grad u, and formally you get x to the 2 kappa plus 1 in the denominator. If you plug this into Laplace u, you get x to the kappa plus 2 in the denominator. When kappa is less than 1, this term is bigger at small scales, so it dominates. Everything should be smooth. This term it's like the friction term is slowing things down, smoothing things out. It's like the heat term, so it should dominate. What's relevant is that when kappa equals 1, these terms have the same, they're both like 1 over x. 1 over x is actually going to play, or sorry, they're both like 1 over x cubed. But 1 over x is going to play kind of an important role in what I'll talk about today. It's a kind of borderline case where the nonlinearity matters.
Did you say what dimension here? 3
Dimension 3 for, yeah, dimension.
1 over x because of the contribution of the volume?
So it'll actually be 1 over x in every dimension. This is a the fact that p is 3 is dimensional. It's actually, if p is the dimension, so if I translate 1 over x into, if I ask what Lebesgue spaces does 1 over x belong to, it just misses LD. So that's actually where the dimensionality is coming in. But let's say everything's 3-dimensional. Okay, so you have local and time well-posedness. And what makes the Navier-Stokes regularity problem so difficult, it's a millennium problem, it's difficult. What makes it so difficult is that the only known a priori conserved quantity for the equations is the kinetic energy. So here we have this energy balance. It says kinetic energy at time t plus all the energy we know, which is dissipated through the viscous term, is equal to the initial kinetic energy. And this quantity which you control is in L2. If it were, it's an L2 base quantity. If it were L3, then you would solve the millennium problem. The fact that it's L2 it's just not strong enough to prove global well-posedness. So this is if I had to express why this problem is so difficult in one slide, this is the slide I would write. Great. So you have trouble proving global well-posedness, but you can still prove that solutions exist. You can prove that there exist weak solutions. This is what Jean Leray did in 1934. Here's a modern version of what he proved. He proved for every initial velocity field in L2, which is divergence-free, and every body force, by the way, I stuck this body force in here, it's on the right-hand side of the equation. And every body force in L1, L2, there's a global in time Leray-Hopf solution. It exists, it solves the equation in the sense of distributions, and it satisfies a version of that energy balance from the previous slide. At finite energy is decreasing. So there's a slight refinement of this notion called suitable weak solution. This satisfies a slightly more powerful version of that energy inequality. But what's important is that these suitable weak solutions, they have partial regularity. Partial regularity says that singularities cannot fill a curve in space-time. So the places where the solution is not smooth. So mathematically we'd say the one-dimensional Hausdorff measure of the set of points where the solution U is not smooth is 0. That measure is 0. Here's a cartoon picture of essentially the whole, almost state-of-the-art of Navier-Stokes regularity theory. So here's the x-axis is a 3-dimensional. Here's time. So let's say you start with some very nice initial data, smooth and compactly, just really nice. Not 0, but nice. Then you start using the Navier-Stokes equations to evolve forward in time. And instantaneously, the solution, even if it didn't start out smooth, becomes smooth. And actually, while the solution remains smooth, there's only one solution to talk about. All the Leray-Hopf solutions agree with the strong solution. We call that weak-strong uniqueness. There's only one object. And you keep evolving until something could happen. I mean, what could happen is that the solution could lose smoothness. If it does so, we say it loses smoothness at t star, the maximal time of smoothness. We don't know whether that can happen. That's the millennium problem. The one that I, have any chance of. Maybe I have equally zero chance of solving, but the one I think about. And you can say that at this time, there are points around which the solution wants to become unbounded. That means the points of infinite velocity. You can prove that. You can't say too much more than that. And these points don't accumulate on a curve in space-time. That was this partial regularity. And after this loss of smoothness, you can continue the solution. You can continue it as a weak solution, a suitable Leray-Hopf weak solution. We do not know whether this can really occur. And we do not know, in particular, after the singularity, if it occurs, would solutions be unique? So this is a central question we're interested in answering. Are solutions unique for all time? The uniqueness is kind of crucial for predictability, because if you can start with one data and have two different solutions emerge out of it, then are you really predicting anything? So uniqueness is a central question. And since all continuations are these Leray-Hopf weak solutions, we're just going to ask the question, are Leray-Hopf weak solutions unique, given a finite energy initial data? That would be the question. We can answer that question today.
So sorry, this t star, you're saying it's always a finite number?
We do not know whether it can be finite.
Okay, so the millennium problem is t star infinite or not?
That's correct. That's correct.
So now you're going to make this assumption that it's finite?
I'm not going to quite do that. What I'm going to do is actually, I'm going to think about what if I started with initial data which was not smooth. Okay. So it's like, what if I prescribe a singularity, and then I'll make some progress. I want to.
Is there any physical reality to these? I mean, is there any, no, I shouldn't say physical reality. Is there like a mathematical perspective on these weak solutions? As what kind of objects do you want them to be?
I would like them to all be smooth and unique. It's really because then I know that I'm talking about something well-defined. Navier-Stokes is self-consistent for all time, and it says you can use it reliably to predict things.
For example, if you prove they're unique and you find a non-smooth one, then you also solve the millennium problem.
Yes, if you find one which starts smooth and ceases to be smooth after some time, then this is a big deal. Yeah. That's it.
All right.
Thank you for the question. No, it's nice to have a conversation. Okay, so I want to say something about. I'm going to spend most of the talk saying kind of negative things about weak solutions. I want to talk about weak solutions, a success story in a particular case. I'm going to talk about weak solutions of Berger's equation. So here's Berger's equation. It models the motion of free particles, which don't interact and they travel. They travel with constant velocity. But this equation, even if you start with smooth initial data, let's say you start with smooth, compactly supported initial data, which isn't zero, then you're going to lose smoothness in finite time. The solutions, they develop jump discontinuities, which we call shocks, and they represent something physical. However, in spite of the discontinuities, in spite of the lack of smoothness, this equation has unique solutions for all time in a particular class of entropy solutions. So in this case, weak solutions are working great. So, and I think for some time people have hoped that one might be able to use not similar techniques, but there's something similar might be true for Navier-Stokes. Maybe I'm going to. I'll mention this point. It's interesting. So this equation, it's like it has the first two terms of Navier-Stokes, just like the acceleration terms. You might want to add the viscous term back in, this heat term. Now, solutions of this equation, viscous burgers, they do not blow up in finite time. They're smooth for all time. And as you take the viscosity term to 0, take epsilon to 0, they actually converge to the unique entropy solution of Burger's equation. So we have a very nice kind of complete picture. There's uniqueness at this level. There's uniqueness at the viscous level, which incorporates more effects. And when you take epsilon to 0, the two solutions agree. So it's a very nice, more or less complete picture.
Any dimension?
This is one dimension only. One dimension only, special to 1D. Scalar conservation laws in any dimension, also good. So there's a generalization. So this is not the only way to regularize Burger's equation. This is the way which probably most resembles Navier-Stokes. But you could regularize Burger's equation by putting this term on here, epsilon squared dx cubed. Now, this would be the KdV equation. It arises as a model for water waves, for example. Now, if you take epsilon to 0, solutions of this equation do not converge to the unique entropy solution of Burger's. So this is David Livermore's thesis at Courant in the 80s. Let's look at some numerical simulations which maybe will convince you of this. So, small caveat, the convention here is that in the drawing all the solutions are negative instead of positive you'd normally think of them. But let's start at the bottom. You're solving the viscous Burgers with some initial data, which the solution, if in the inviscid problem, it would shock between these two frames. This is the viscous problem, so it remains smooth, but it develops a very large, very large slope. Okay, so it remains smooth, and you continue to evolve. If you study the dispersive regularization instead, then okay, this is where the solution remains smooth. This is where it would shock in the inviscid problem, and it becomes highly oscillatory after the time where the inviscid problem would shock. So when you send epsilon to 0, these solutions weakly converge to this kind of envelope. And if you take epsilon to 0, this will weakly converge to something which looks like this. Oh, sorry, well, it depends on the topology. It will converge to something which looks like this. And these profiles are not the same. So this is numerical evidence that the kind of regularization you put on it really matters. And the way we think about this is that you're adding on, it's like when you regularize the model, you're adding on more, you're trying to make the model more physical by capturing more effects.
Did you say what weak topology you're using?
I didn't, and because it's not important for weakly in L2 for this, and strong in some topologies for this one. Yeah. So in any case, the kind of regularization matters, and I'll come back to this by the end. Great. So there's been over the past decade, there's been mounting evidence in support of non-uniqueness. But already in 1969, Leray-Hopf constructed a kind of example of non-uniqueness, and it's for Navier-Stokes, but it has some caveats. One of the caveats is that, really the main caveat is that her solutions, they live in a time-dependent domain. As time goes to 0, the domain shrinks to a point. So this is a very non-standard initial boundary value problem. What she really takes issue with is that she's not using the usual no-slip conditions on the boundary. So that's what she really takes issue with. But already she had some examples in conjectured non-uniqueness. Some people refer to this non-uniqueness of Leray solutions as Leray-Hopf conjecture. And for many years there was essentially no progress on this. In the last 10 years we've seen a lot of progress. It can essentially be organized into two programs. The first program is work of Jia-SvÄ and k-Guillod, and I'm going to explain that in some detail, but it's kind of, there's something unsatisfactory about it, which is that it produced compelling numerical evidence of non-unique Leray solutions with some theory, but there's no real definitive proof. You can kind of convince yourself of what's true, but it's not really proven. On the other hand, recently there have been these convex integration constructions which have attracted a lot of attention. Not just for non-uniqueness, but also for for the relationship with work of Lars-Onsager, Onsager's conjecture. Theo can tell you more. It won't be the focus of today's talk. But in work in the Annals in 2019, Buckmaster and Vickel, they were able to construct non-unique weak solutions of the Navier-Stokes equations, but they don't belong to the Leray class. They don't satisfy the energy inequality. They just satisfy the equation in sensitive distributions. So these you can really prove, but they're not Leray solutions. And we think that all physically reasonable solutions are at least Leray solutions. So take that as you will. So these programs are kind of remain to be completed, if you like. So here's what we're able to do. We are able to show that there exists a one-parameter family of distinct suitable Leray-Hopf solutions to the Navier-Stokes equations. They have identical body force on the right-hand side, and they have identical initial velocity, which is actually 0. So the force really matters here. The force is not smooth, but belongs to this class. And since the initial velocity is 0, you can imagine it plays an important role in the proof. But this is joint work with A BruÄ Maria Colombo, which appeared in the Annals last year.
Can you indicate with your hand what L1 and L2 means? I mean, not what the formula. I'm just like.
Yeah, it means that the kinetic energy, the square. I mean, it's integrable.
L2 and X and.
Yeah. So what's the
norm is L1 and T.
The L2 norm is L1 and T. That's right. The L2 norm of space is L1 of time.
So
yeah.
1,000 little kids stirring the fluid in different places and stuff.
It could be quite irregular. I will say this. Our force, I've written this space on here for simplicity, but our force is actually this. It's actually L1T, L3 minus X, so it doesn't quite hit L3. The point is, if you're actually to make our force any smoother, solutions would be unique. So it's a borderline result. It's not exactly reflected in this, but it's a borderline result. So
there's a theorem just beyond.
There's a theorem on the other side just beyond what we prove.
You show that that's sharp.
That we show that that's sharp. Exactly. Yeah.
The body force means like things shaking somehow and starts out flat.
Yeah. Kids stirring, or like invisible. It's
Ghosts.
Yeah, ghosts. So, but I mean, like there really are forces that act on fluids. If the fluid, for example, the fluids. I mean, gravity for one, but if the fluid's magnetized, for example, then. So that
If that 2 were a 3, you couldn't have.
If that 2 were a 3, everything would be smooth and unique. Or let's say let's say that. Yeah. Okay. I'm going to spend a lot of time talking about this theorem. I want to devote a little time to talking about other people's work as well. But part of this is that this talk arises out of a job talk I gave, and so there's, I spent a lot of time trying to say that, hey, you should hire me. So I've actually talked more about my work than I normally would like to. So I'm going to try to highlight the work of some other people. I want to first talk about self-similarity, which plays an important role in the proof. The Navier-Stokes has a scaling symmetry. I mean, it has some obvious kind of more standard symmetries, time translation, space translation, reflection symmetry, things like this. But it has a scaling symmetry. Here it is. If I have a solution U, and a body force capital U, and a parameter lambda, and I define U sub lambda, F sub lambda like this, I'll get another solution. But importantly, this lets me zoom in and zoom out on solutions using this transformation. So this will be useful. We're going to talk about self-similar solutions, which are invariant under this symmetry. These solutions can all be written, so if U is a self-similar solution, then U of xt, you can rewrite it as 1 over root t of capital U. Capital U is a function of x over root t, which is a dimensionless spatial variable. And you can rewrite the body force as 1 over t to the 3/2 capital F. F is a function of the new variable. So why would you do this? I mean, because, well, you can reduce the problem by one dimension, and maybe you can win that way. And so Leray in 1934, he understood this transformation, and he proposed a version of this as a possible ansatz for singularity formation. But this is kind of something that actually later it was shown that the solutions he proposed to exist don't exist. But the idea for this change of variables is quite old. We didn't come up with it. So now you have an equation for capital U. Here's the equation, and it looks a lot like the usual Navier-Stokes equations. It has some additional terms. Here they are. They come from the time derivative. When the time derivative hits 1 over root t, you pick up this minus 1/2 term. When the time derivative hits capital U, you'll pick up this term. Or rather, when the time derivative goes inside and use the chain rule, etc. So these are the equations for the similarity profile. The initial condition becomes a kind of boundary condition at spatial infinity. In any case, these are the solutions we're going to think about a little bit. What do you do with these solutions, by the way? What you do is you say, I'm going to try to solve Navier-Stokes with initial data which is self-similar. So self-similar initial data, it looks like 1 over x. It's singular. There's no uniqueness for this kind of data. It actually lives just on the borderline of the uniqueness theory. That's why you're interested in these solutions. So I'm going to say, I'm going to try to solve Navier-Stokes with initial data, which is self-similar. I should get a self-similar solution. These reduce the problem by 1 dimension. Maybe I'll be able to understand everything. Okay, so this was an idea of Vladimir Šverák, who was my advisor at University of Minnesota. And he studied the problem without a force, which is kind of the more ideal setting. And here was the picture. So he said, you fix some initial data. There appears to be no chalk, because it's right here. But you fix some initial data. I'm calling it A naught, which is like 1 over x. Okay? And you're going to solve the problem with this as initial data, but you're going to multiply it by a number, sigma, which is a parameter that you're going to play with. And when sigma is 0, you're very good at solving Navier-Stokes, because the initial data 0 is the 0 solution. What you do is you start to increase the sigma parameter, and you see what happens. So the picture is something like this. All right, so here's the sigma parameter. Here's x. Solutions are living in this function space. When sigma is 0, your solution is the 0 solution. As you start to increase sigma, you get a curve of solutions in the function space. And they're all self-similar solutions.
Sorry, you get a curve of solutions in the function. In
the function space. So I mean,
it's like just one solution in the function space for each.
Well, so for every sigma, yeah, I get for every sigma. So it's a curve in the parameter sigma. So they're all solutions. They have different data. Yeah, I'm increasing the initial data. So you have this curve, and you can basically ask this question: is there some kind of bifurcation? Is there some other curve of solutions which intersects this one or kind of emerges out of this one? For example, some kind of pitchfork bifurcation like this. And Jia and Šverák, they asked this question, and they said they actually just supposed that this could happen. Suppose there's some kind of bifurcation. Then you get, what that tells you is you're getting multiple Navier-Stokes solutions from the same, multiple self-similar solutions of Navier-Stokes from the same self-similar initial data. That's their picture. This was kind of their non-uniqueness scenario. They couldn't prove it though, so they supposed that it happened, and then they're able to say that there's non-uniqueness of Leray solutions. There's something non-trivial here because these self-similar solutions, they don't have finite energy. They're like 1 over x, which is not square integrable in 3D. But if you truncate their solutions, then you do get something finite energy. So they suppose this. Now, it's very difficult to study this problem kind of by hand, but you can put it on the computer. That's what they did. And here's what they find. So you choose your initial data, which is, right, it's singular data, it's self-similar, and you're going to kind of grow it they choose it to have a reflection symmetry across the z equals 0 plane. And as you increase sigma, when sigma is about 300, you find a pitchfork bifurcation, which looks like this, which breaks the reflection symmetry. So what we're looking at here, we're looking at one component of the solutions. Here's the z equals 0 plane. Here's one of the symmetric solutions. Here's one of the non-symmetric ones. And there's one more non-symmetric one which bends down. So this is the picture that they find numerically. What we're looking at here is a plot of the eigenvalues of the linearized operator. So we find that here, one of the eigenvalues becomes unstable. Okay. Any questions on this?
When you first time see it, you kind of want to say, okay, probably some numerics went wrong, and you want to fix it.
Well,
unless you know all the...
Well, because here's the thing, though. These numerics are all done at the level of smooth solutions. So these self-similar solutions, all you do is you simulate. They solve an elliptic problem, and they're actually provably smooth. So I don't know. Vladimir told me they're kind of like 3 levels of numerics. So I can waste some time by telling you this. I think it's interesting. The first level of numerics is kind of like you just do numerics. If you're trying to do singularity formation that way, then near the singularity, you're never going to be able to fully resolve everything. You need too many grid points. I mean, you don't know whether if you go forward a little more in time, whether it's going to just disappear. There's another level, which is that everything that you're simulating is smooth, and this is somehow more believable, but it's not a proof. That's the level this lives at. Then the last level is computer-assisted proof. So, anyways, this is at level 2. I don't know if there are any numerical analysts in the audience. Maybe you agree with this, maybe you disagree. Yeah. Okay, so this is the picture. Now, this bifurcation is it's not a Hopf bifurcation, it's a pitchfork. It's reminiscent of that bifurcation to vortex shedding that we saw earlier. This is kind of no mistake. There are a lot of analogies between the problems, and they're both difficult. That every physicist who studied fluid dynamics knows that there's a Hopf bifurcation to vortex shedding, but that's not a theorem. This is also not a theorem, and part of what makes it so difficult is that these solutions are not explicit. You can't really get your hands on them, and then write them down, and then compute something about the linearized operator. They kind of just are, but we don't have a good description of them. This makes the problem very difficult. I will tell you about a solution in 2 slides. I'll tell you about a solution to this. So just like in the Hopf bifurcation, I was talking about, some of these solutions are stable, some of them are unstable. I want to say something similar here. But first, I need to kind of say something about what that means. These self-similar solutions, they're not steady states of Navier-Stokes. They're steady states of Navier-Stokes in a new set of variables called self-similarity variables. And this is the change of variables. So there's a way to visualize this, actually. So you might think here's the c variable. This is x over root t. Here's the tau variable. It's log time. This is the new time variable, which enters here. So d tau u is this thing. So in these variables, if you have like some straight lines, then and they get mapped to the physical variables. Then here's x, here's t. These straight lines, they look like a parabola. So things that are kind of, and by the way, tau is log t. So t is greater than 0. Tau runs in all the real numbers. And as tau goes to minus infinity, little t goes to 0. So this is the change of variables that you make. In these variables, self-similar solutions are steady states. And what's so important about this change of variables is that for solutions which look nice in these variables, like they're order 1 and they're smooth and stuff, in the physical variables, they live exactly on the borderline for proving uniqueness. If you're smooth in these variables, then you're actually not smooth in these variables, but you're just on the borderline for the standard theory. So, okay. So, what we do to handle the problem of the solutions not being explicit is we do this. We can make them explicit if you allow yourself the flexibility of a body force. So the perspective you can take is this. Suppose that you have any velocity field. You can say that that velocity field solves Navier-Stokes with a certain force, and the force is just what you get on the right-hand side when you plug the velocity field in. This may sound stupid. This may sound like cheating. This is actually what many numerical analysts use to verify their numerics, because this lets you generate explicit solutions, and you can use this to kind of benchmark and make sure everything's working. So they call it method of manufactured solutions or method of engineered solutions. We're also going to use this trick. It lets you choose your solution, or lets you, in our case, choose your self-similarity profile. So what I need to do is I need to choose a capital U bar. It's going to be a steady state of Navier-Stokes in the new variables. And I need to choose it so that it's unstable. Something like the pictures we saw in the previous slides. I'm not going to be exactly tracking a kind of bifurcation. It's enough to know that this capital U bar is unstable for self-similarity Navier-Stokes. In that case, you can kind of get any perturbation of this capital U bar will actually kind of, well, it'll kind of spiral out of control and will lead to non-uniqueness. The specific construction is through the unstable manifold of capital U bar. So solutions on this unstable manifold, they converge to U bar in exponentially in backward time. So it's like backward time in this picture. But in this picture, that's like saying they converge to the initial data, or they converge to the self-similar solution as t goes to 0. So there's a kind of compression of infinite time here to finite time here. But I don't want to spend too much time on this because I actually want to show some pictures. I mean, I want to say a little bit about how you find the unstable solutions, but okay. So this you can reduce your whole question to finding one of these unstable solutions. Then
We're constructing some solution on the unstable manifold and extending it somehow, or
to complete the proof, once you have an unstable steady state in these variables, if you construct the unstable manifold, every trajectory on that manifold corresponds to a non-unique solution, because you have an exact solution, capital U bar. Then you have all these solutions which are kind of emerging out of it, in backward time. But in the physical picture, that means that at time 0 they're separating, because the unstable manifold construction, it normally takes infinite time, but time is log t, so it gets compressed. So every trajectory on an unstable manifold is one of these non-unique solutions. I want to go farther. I can draw a picture at the end. All right. So I still need to find such an unstable solution. Technically, what you're finding is an unstable solution of Navier-Stokes in these self-similarity variables. It seems very complicated. Things would be a lot simpler if you could drop a few terms in the equation. And you can actually do this. I mean, there's some heuristics for this. I get to kind of choose my solution, and so I can choose it in such a way that certain terms dominate. But I'm just going to say, suppose I can drop these terms in the linearized operator. Suppose I can drop like the viscous term and this term which comes from the change of variables. Then all I would need to do is find an unstable steady state of Euler in 3 dimensions with a couple caveats, like it should have an unstable eigenvalue and then things like this. And you think to yourself, Euler's one of the first PDEs ever written down, so this should be kind of known. And you start poking around the literature and asking people. And then you find, at least in terms of rigorous mathematics, let me qualify this statement a little bit, no steady state of 3D Euler was known satisfying what we need. It needs to be smooth and decay, have an unstable eigenvalue. And so you have to find one and construct it. So that was kind of remarkable that this was not known. In 2D, there are explicit steady states, vortices, and the study of their stability is very classical. But that's in 2D, and you would like to put something in 3D, and you could just say, take the 2D steady state and extend it by one dimension. Wouldn't you be done? There's a difficulty with that because we want our solutions to have finite energy. And if you extend it by one dimension, it's going to have infinite energy. So this is an issue. But at the core of our proof, we use these vortices, these explicit steady states. If you're a little particle in a vortex, then you just get swung around the origin with some speed, and this is what they look like. So in 2018, Misha Vishik at UT Austin, he proved this seemingly innocuous theorem. There's a smooth, unstable vortex. And we make some adjustment. You can actually find it to be compactly supported. This paper is kind of funny. I mean, so Vishik, is kind of well known in the mathematical fluids community, but he, basically he posted 2 papers together over 100 pages on the archive, and they're written in Microsoft Word, and they're kind of difficult to understand, but people knew that they should be important somehow. I mean, he's a well-respected member of the community, but people didn't really understand them. So there's a little story here, which is that I started my postdoc during COVID, and I was actually at NYU, but we didn't want to live in New York City during kind of height of COVID, so we moved to Princeton, which we knew we were gonna move there in a year. And Camilo Delelis at the Institute for Advanced Study knew that I was in town. He asked me to take part in this reading group on Vishik's papers. He said, these seem important, people don't understand them, and we're just going to read them and write notes on it and try to process it. At the end, we'll put the notes out for everyone to see. So we start reading Vishik's theorem, and pretty soon we realized that there were a lot of analogies that you could make with work of Jia-SvÄ, and that kind of the fundamental strategy was the same. And so after kind of absorbing this, a subset of us got emboldened to try to study this 3D Navier-Stokes non-uniqueness problem. So the lecture note, there are 7 of us in this reading group, and we did put the lecture notes on archive. They're by A, B, C, D, G, J, K. So I'm A. I'm Albritton. So, but in any case, so what Vishik proved is his own non-uniqueness theorem, but it was for 2D Euler instead of 3D Navier-Stokes. There are a few jumps you need to make in order to get to 3D Navier-Stokes. I want to mention one thing very quickly, which is that there are kind of 2 categories you can think about. You can think about these non-uniqueness theorems for Navier-Stokes, like what I'm working on, and you can think of non-uniqueness theorems for Euler. Okay, this is one category, Navier-Stokes versus Euler. Another category you can think of is forced versus unforced. So the forced stuff is stuff you can prove by hand. You have enough force gives you enough flexibility to prove something. The unforced category at the moment is all numerical. So for 2D Euler, there's also a numerical study without forcing of a possible non-uniqueness scenario. I included the numerics here. I'm not sure I quite have time to talk about them, but in detail. But this is work of Alberto Bressan and co-authors. He's at Penn State, and what he finds is in a particular scenario for 2D Euler, you can have 2 different self-similar solutions that arise from the same self-similar initial data, very similar to Jia-SvÄ. So this is currently just at the level of what I consider to be good numerics. This is the similarity profile at time 1 for one of the solutions. This is the similarity profile at time 1 for the other solution. They come from the same data. All right, so our construction is based on the construction of an unstable vortex ring. Vortex rings are real objects. Here's one. This is a vortex ring of steam above Mount Etna in Italy. And you might say, why did you make it so small? And I like to say, because I didn't want to cut out the very beautiful mountain and offend my Italian collaborators. So this is a vortex ring of steam. It kind of travels with constant velocity. And it remains coherent for a very long time. Mathematically, schematically, it looks like axisymmetric, which means it's best written in cylindrical coordinates. And the vorticity is supported in a core here, which is very far away from the z-axis. So if you were to draw this thing, we call it a vortex ring of small aspect ratio. It's like the core is all the way out here, and it's swung around like this. Now, the study of these vortex rings of small aspect ratio, we didn't come up with that. That goes back to Kelvin and Helmholtz, early days of hydrodynamics. It's classical, but they're the right objects for our construction, because hiding within 3D axisymmetric Euler with no swirl is 2D Euler. And we have one of these unstable steady states for 2D Euler. And okay, I've written some equations here. I don't really parse everything. That's not the point of this. The point of this is that there are a lot of terms that have 1 over r. So r is the distance to the z-axis. And if you forget these terms, then you just get 2D Euler. So 2D Euler is hiding at large distances in 3D Euler. And once you have this observation, then you can think this. I have an unstable object for 2D. I have a perturbative way to put it into 3D and keep it unstable. So this is what we did, basically. I mean, we take Vishik's unstable vortex, which, when you dig through enough, Vishik's unstable vortex, which you read about in Camilo de Ellis' reading group at the IIS. And you take it, it's like here, it's swirling down here, and you just take it to be the core of your vortex ring. You just put it in there. And it doesn't really solve 3D Euler. It solves it with a force, but we're letting ourselves have forces today. This is actually probably the part of the proof where you could remove the force. At that point, you've constructed the ring. You need to show that what you've constructed is still unstable. And then you trace through kind of all these connections that I've been drawing, and you fill in all the details, and you have the proof. So I'm going to write a few things that we should also not parse, but to just give it an appreciation for what you have to do. You write the linearized operator around Vishik's vortex. You write the linearized operator around the thing you constructed. You need to relate them. You have an unstable eigenvalue for this one. You want to try to get an unstable eigenvalue for that one. And there's a spectral perturbation argument that you do. I'm comparing the resolvents of the two different operators and showing some convergence result by hand. And this shows that the unstable eigenvalue doesn't disappear when you put the vortex into 3D. So this is the scheme. Then you have the unstable steady state. You put it in self-similarity variables, and you construct the unstable manifold, and you get it. So Theo, we started late, so I don't know how much time to take.
5 minutes.
5 minutes, sounds good. All right, so I want to conclude in 5 minutes. Let me just address some obvious things. Our construction has a force on the right-hand side. The ideal picture, there's no force. Everything comes from the initial data, and people often ask, can you remove the force? I don't know how to remove the force. There's been some discussion in the literature about maybe you can remove it if you use computer-assisted techniques. That's very interesting. It's not what I'm working on. There are some related questions about other models, which are still very interesting, but for which you actually have a hope to remove the force by hand. And here are some of those. Here are some of these questions. But let me focus on this question, which I think is very interesting. You might think, this guy is finding non-unique solutions. What does this have to do with anything? You know, do these really exist? Is this physical? So you can ask, in general, what are the implications of these non-uniqueness constructions for physics? I think it's a very important question. And the physicists are already thinking about this because they're not constrained by the need to prove everything. They can just make observations and try to understand. So I'm going to say something about a case study that they've addressed. It's non-uniqueness in the inviscid limit to a vortex sheet. So I think we have time for a little. Movie. All right. So what are we looking at? We're looking at a 2D fluid simulation where above this layer, the flow is moving to the left with some constant velocity. And in this layer, the flow is moving to the right with some constant velocity. And there's a sharp jump. It's numerical, so it's a nearly sharp jump. And you touch this thing. You just touch it ever so slightly. Here's what happens. So let's watch this again. You touch it ever so slightly. At first, the solution has these very small scale structures. These structures develop, interact with each other. They're essentially little vortices. They merge, and then they form larger. And this keeps happening. This keeps happening until the process is, as much as it can. Keeps happening. These things combine. This is a classical instability. This is called Kelvin-Helmholtz. Now, related to last week's colloquium talk, Alexei Malebeyev did a numerical study of Kelvin-Helmholtz instability. Like many others. And he had this idea, also with co-authors Beck, Simon Talebard and Jeremy Beck, about how how Kelvin-Helmholtz is a mechanism for instability and how really near this solution there should be no good uniqueness class, but that there might be some measure of solutions which is unique, some generalized stochastic notion. There's a clear mechanism for instability here, mechanism for non-uniqueness here, in that these perturbations at very small scales can travel up to large scales. And if you do many simulations of this, the exact details of what's going on are essentially unpredictable. They happen at very small scales, and they all look a little bit different. But macroscopically, all the solutions look more or less the same. And this is a way to resolve this non-uniqueness question in your mind. Okay, so if things are really so sensitive to disturbances at small scale, and those disturbances can travel up to large scales in finite time, shouldn't we be living in this, absolutely chaotic world? But the point here, one of the points here is that the behavior at macroscopic scales looks all essentially the same. All right. We're not going to spend too much time on this, but the constructions that we've talked about today, and also this Kelvin-Helmholtz instability, they all fall under the umbrella of non-uniqueness as an extreme form of instability. When you think of usual instability, what you normally think of is you make some finite amplitude perturbation, and then you wait some finite time, and solutions move away from each other. This is more extreme somehow. Non-uniqueness is like you make an infinitesimal perturbation, then you wait no time, and the solutions are driven apart instantaneously. When you say it like that, it really does sound like it's an extreme version of, non-uniqueness is an extreme version of instability. And already in 1969, Lorenz in his paper, Predictability of a Flow which Possesses Many Scales of Motion, recently people have been revisiting this, revisiting this quote in particular. It seems that Lorenz, he had this vision already, not just of what we think of as the standard butterfly effect, which is we think of chaos as butterfly effect, sensitive dependence on initial conditions, but it seems that he already envisioned actual non-uniqueness, actual unpredictability, and so this has been revisited in recent years, and I view what we're doing, these non-uniqueness constructions and the relationship with hydrodynamic instability, is actually falling within this kind of framework. But from the perspective of rigorous mathematics, there's almost nothing known about this. So I think this is a program for 10 or 20 years to understand this and what exactly it has to do with the physics. And in any case, thanks very much.